Hey everyone, welcome back to Abstract Algebra 1. This will be lecture 3 of the course. And in this section, we're going to take a look at a sort of a tangible example of a group. And it's really a classic example of a group. And I think this lecture will feel like the least like a math lecture. And then after this one, we'll probably return to form in the main. But the goal here is really to develop some physical intuition about a group and to see some of the properties of groups kind of firsthand, just to prime you for the next section, which will be kind of the definition of a group and additional examples. So let's go ahead and get started. We'll call this section 2.1, and it's going to be Introduction to Groups. And we're going to be talking about the symmetries of squares, symmetries of a square, and technically we'll be discussing what's called the dihedral group. Okay, and so as I said, this is a very classic example of a group, and here's how we're going to develop it. There's going to be a lot of colors flying around here, so I apologize to anybody who might be colorblind. I don't know any other better way to present this group than this. So what we want to do is we want to imagine a square, and we're going to think of the square as being transparent. Maybe it's made of glass. Okay, so we've got a square. Okay, transparent square made of maybe glass with the corners having a different color. Each corner having a different color. So we'll have the pink corner over here. We'll have, that looks kind of orange, but that's pink. We'll have the orange corner here, the green corner, and the blue corner. Okay, so we've got the square here. And so with this way of marking it, this marking scheme, our understanding is that, you know, the square is also with the understanding that the square is transparent, we're in a position to describe basically all possible ways in which the square can be repositioned. So the name of the game here is you've got a square, it's transparent, each corner is colored. You can just think of those as a label, right? And given the fact that it's transparent and that the corners are all colored / labeled, we are going to be interested in all of the different ways that we can reposition the square relative to this starting position. Okay. So our goal is to identify all of the possible repositionings of the square. Okay, so our goal is to consider all of the possible repositionings of the square. Now we're going to take our time with this. We're really going to take our time and make sure that we get a good physical intuition. I mean, this will be an hour-long lecture just like everything else. At the end of the lecture, I think you will have a good physical sense for what is going on with this group. Okay, so we're going to kind of start with this statement: the motion of the square, no matter how complicated, is equivalent to one of these 8 motions. Okay, so there's fundamentally 8 motions that we can apply to this square, and we're going to list them all right now. Okay, so the first one we're going to denote as R0. Okay, and this one is a rotation of 0 degrees. Okay, and so I'm going to really strain to make everything very clear, which means I'm going to write everything down a lot of different examples being written down. So in an R0, right, if this is my pink corner, then my pink corner stays. If this is my orange corner stays. All right, green stays. Rotation of 0 degrees, right? It's not moving, so it's just going to stay in its original position. Okay, that's kind of the very obvious rotation of 0 degrees. The next one will be, we'll call it R90. This will be a rotation of 90 degrees. Okay, so here's where things start to get a little more interesting. This will be R90. It takes the square from its starting position, right? Pink is here, and a 90-degree rotation would be like this, right? In the counterclockwise direction. So this would rotate from up top to down at the bottom. And the orange would go from here to here. The green starts out here, and it's going to rotate over, right? So it's going to go here. And the blue starts out down here. This is the original position. It's going to rotate up. There's R90. Okay. R180 is a rotation of 180 degrees. Okay. Okay, so R180. Okay, so again, pink starts here, and then it goes not 90 degrees, but another 290 degrees, basically, right? So it ends up down in the opposite corner. Orange was here, and it would rotate 2 places. Green, again, rotates 2 places, up here. And then the blue, like that. Okay, so hopefully this is clear, right? The pink goes from here, that would be from here to the bottom would be 90 degrees, and then another 90 degrees would put it here, which is where it lands. Okay, and then the final of the rotations is R270. So this is like a 270 degree rotation. Okay. R270. And so this one, very similar, right? So pink is here. So it'd be 90, 180, 270. So it's going to end up here, isn't it? And then orange starts here, and it's going to end up down here, kind of behind the pink. Green would go to, let's see, 1, 2, 3, yep, up there. And then the blue would go 1, 2, right there. Okay. Oh, that's supposed to be over in the corner a little more. Got a little carried away there. Okay. All right, so those are the 4 rotations. So R0, R90, R180, and R270. We'll use this notation to describe this motion. Okay, but there's 4 more that we need to worry about. So what are the other 4? Well, the next one we're going to call H, and that's going to be a flip about a horizontal axis. Flip about a horizontal axis. Okay, and so what's H do? Well, H, we start, again, our pink is here. Now, here we're talking about a horizontal axis. So this is what we mean. Okay. So the horizontal axis will be, so pink will start up here, and it'll flip down to here, won't it? Orange will start up here, and it'll flip down below. Green would be here. It's going to flip up to the top. And then blue starts here and flips up to the top, right? So you can see that this just flipped. And this would be equivalent to basically like flipping the square over. Okay. And then we're going to have the next movement will be called V, and that'll be a flip about a vertical axis. So hopefully you're following along here, and maybe you've got your markers out and or you could just be using letters, pink, P for pink, O for orange, etc. All right, and so in this case, the axis is vertical, so it's going to flip it like this. All right, and so your pink starts out here, and it flips over to here. And orange starts out here, but it flips over to here. Okay, green starts here and ends up over here. And blue is here and goes to here. All right. And so that's a vertical flip. And the next one is, we're going to call it D, and that's a flip about the main diagonal. And what do we mean by that? Well, that one is, when we say main diagonal, you kind of think back to your linear algebra. We're talking about this diagonal here. Okay, and so pink is here. It's on the diagonal, so if I flip it on the diagonal, it's going to stay put, isn't it? It's not moving. The orange is over here. Now that guy is going to flip down, isn't it? It's going to end up down in this spot. The green starts here and it flips up into that spot. And then the blue is on the main diagonal, so it too will stay put with this move. And then the last one, the last movement is we're going to call it D prime, and it's again going to be a diagonal flip, but it's going to be the flip about the other diagonal. We'll just say the other diagonal, the non-main diagonal. All right, so D prime does this. All right, it's going to flip along this guy. Okay, so pink would flip this time down to there. Green is fixed. Orange also fixed. It doesn't move. And blue starts out down below and flips up. It basically swaps places with the pink, doesn't it? Okay. Perfect. So these are the 8 motions. Right, and so our initial statement was that no matter how complicated the motion of the square is, it's ultimately going to be equivalent to one of these motions. Okay, so let's, starting with these as kind of the backdrop here, let's look closer. Let's look closer at how every motion is essentially equal to one of the 8 we just laid out. Okay, so let's look closer at that. Okay, so suppose we begin with our given square, and we perform a 90-degree rotation followed by a flip about the horizontal axis. Okay, so we start with our original square. Then we perform a 90-degree rotation. Followed by a horizontal flip. Okay, so basically we have our square, and we're going to do an R90 to it, and then after we do the R90, we're going to do an H. Okay, so let's see what happens here. So we start with pink up here. I mean, I think I might just put them all on really first. Pink, orange, green, and blue. Okay, so what happens to pink when we do the R90? Well, it goes down here, and the orange goes up here, and the blue is here, and the green is here. There's our 90, right? So we basically just twisted it 90 degrees. And now the horizontal flip, what happens with the horizontal flip? So remember, horizontal flip is like this. All right, so pink is going to come back up to the top. Green is going to come back, this one down here is going to flip up to here. Orange is up at the top, it's going to flip down to the bottom. And then the blue will do the same. Okay. And so this is our first example. So we did a R90 followed by an H. Now, if we were to look back at our previous examples, we could see that this two-step motion is actually equivalent to a single motion. So this two-step motion is actually equivalent to a single motion, and the single motion happens to be a D. Let's see that if that's true. Right, so we remember what D looked like. Let's write this one out again. So pink was here. So D is a main diagonal flip, right? Remember that. Okay, so pink starts out here, and since it's a main diagonal flip, it's fixed. Green starts out down here. Since it's a main diagonal flip, it pops up here. Blue is fixed. And orange starts out up top, and it's a diagonal flip, so it pops down to the bottom. Right? And so you can see that these two squares are equal. They're the same, right? Okay, so given what we've just seen here, it's good for us to, we can say that H followed by an R90 is equal to a D. Okay, so H composed with an R90 is equal to a D, right? And the order here is, I think of it as kind of, as like almost like a function, right? The argument would be on this side, so what you want to happen first needs to be on the right hand side. So the R90 comes first, and then we do the H. Okay, so R90 and then H. That's kind of the reverse of the way you would write it if we were drawing the arrows here, but R90 followed by an H equals a D. And that's what we can see there. All right. Very cool. Okay, so we're just kind of starting to scratch the surface of the idea that when you compose a bunch of these, you get one that you already had. So what about if we do an H followed by a V, so a horizontal flip followed by a vertical flip followed by an R90. Okay. And so these are, one second. So we're going to do horizontal flip, and then vertical flip, and then an R90. Okay, so we'll just kind of do this a little faster. So pink's here, and then I do a horizontal flip, and it comes down here, and then I do a vertical flip, and it's going to pop over there, right? So I guess I should maybe put the other vertical here just so we know. Okay, and then R90 is going to bring it from here up to the top. Right, so that's how pink is going to flow through. Orange is going to be here. Horizontal flip drops it down to here. Vertical flip brings it here, and then a 90-degree rotation puts it there. Okay, what about green? Green starts out down below. Horizontal flip brings it to the top, so here we're flipping it up and it goes to there, and then we got to flip it across the horizontal or the vertical, and then it lands over there, and then a 90-degree rotation makes it move from here over. Okay, and then blue is going to be basically everything else. Okay, and so if you look back at our initial 8, we could see that this is actually So this would be a, let's see, so an R90 composed of a V composed of an H. And what does it equal? Well, it turns out that this is all equivalent to an R270. And let's see, so pink starts here, 270-degree rotation. It's 1, 2, 3 motions. Orange starts out here, right? Green goes from here up to the top, and blue looks like that, right? And so you can see that these are the same. Okay, so an R90 composed of a V composed of an H is equal to an R270. Okay. All right, and so this is part of, I mean, this is a group, right? Actually, these 8 motions, these 8 motions, let's write them out. So R0, R90, R180, R270, and then HVD prime. These 8 motions, together with the operation of composition. Okay, so these 8 motions together with the operation composition, meaning you can combine them, right, form a mathematical system called the dihedral group, and specifically of order 8. Okay, so the dihedral group of order 8. Okay, and so when we say of order 8, that just means there's 8 elements in the group. Okay. Okay, and so this is our first example of a group. Okay, and this is obviously it's a dihedral group, so it's got a name, right? And so it's a famous group. It's denoted by D4. Okay, D4. Now, the next thing, there's a fascinating structure to this group, and we want to explore it a little bit, but it's going to be ever so slightly labor intensive, and I'm going to ask you to bear with me. So what we're going to do is we're going to build an operation table. Okay. This group has an interesting structure, and an operation table is useful in seeing the structure. Okay, so we're going to build this table quick. Okay. And so this will be slightly labor intensive. If it's too much to endure watching it, you can obviously pause the video or advance the video through it if you like. But basically what we're going to do, it's going to be kind of like you can think of it kind of like a multiplication table you maybe saw when you were younger. But across the top we'll have R0, R90, R180, R270, and then HVD prime. And then down the side we'll have the same R0, R90, R180, HV, or R270, HVD prime. Okay, I'm trying to get everything. Well, that's all right. Okay, and so the idea here is that if I do an R0 followed by an R0, I get R0. If I do an R0 followed by an R90, I get an R90, right? And so the first the first row is really just everything composed of an R0. Yeah. Hold on, let me make sure that I've got the order right here. So H followed by R90. Okay, so here it'd be an R0 composed of an R90, right? So this entry here would be read as R0, R90. So this first, and then this top first, and then this vertical. So this would be an R180. You can see anything you do, anytime you compose anything with an R0, you get basically the original thing. Okay, so that's what that row would look like. And now what happens when we move to the next row? So here we're doing an R0 followed by an R90, right? So that's going to be an R90, obviously. What about an R90 followed by an R90? Well, that's an R180. A 180 followed by a 90 is a 270. And what about a 270 followed by a 90? Well, if you've gotten 270 degrees, then another 90 is just 360 degrees, so you're back where you started. Okay. And now, what about a horizontal flip followed by an R90? Well, that turns out to be a D prime. Okay, and then this one is a D, and then you've got an H and a V. Right, so if you do a main diagonal flip followed by a 90-degree rotation, that's equivalent to a horizontal flip. Right, so it's kind of fascinating. Right, so these lines are it's showing you the structure already. You can kind of see everything's kind of cycling down, right? So these all cycle, right? The R0 goes to the end, everything else slides down, and these cycle as well. Kind of, well, no, these are doing something slightly different. So the D prime comes down, the H, yeah. So it's a little different over here. They're actually shuffling in a different way. But we'll see the structure as we get more of the rows filled out. So what about a 0 followed by a 180? That's a 180. A 90 followed by a 180 is an R270. And then you've got a 180 and a 180 is an R0. And then you've naturally got the R90 here. Okay. And then over here you've got V, H, D prime D. Okay. And then the 270. Right, and then the R0, and then the R90, and then the R180. Okay, now what's going on here would be a D, D prime, V, H. So I'm kind of writing them out at this point. Okay, so that's the upper half, right? So far we've been just composing all of we've taken all of the motions and composed them with just the rotations. Now what happens when we start to compose them with the flips? Okay, what happens there? Right, so we've got an H composed of an R0, and that's going to give you an H. An H composed of an R90 is going to give you a D. So that's a main diagonal flip. A 180 followed by an H is a V, vertical flip, and then you've got the D prime here. Now what happens over here? So if I do a horizontal and a horizontal, I actually get back to where I started, and that's an R0. If I do a vertical and then a horizontal, I actually end up doing a 180. Okay, and then an R90 is here, and an R270 is here. Okay. Right, so here the rotations aren't simply moving in order. Right, well, the order's out, they're out of order actually, but they will actually, let's go to the next line and we'll see what happens here. So I've got a V, D prime, H, D. Okay, so the D's are changing. So the D went here, the D prime went there, the D's and the D prime replace one another here, and then the H's and the V's swap positions as well. Very interesting. And then over here, everything is actually cycling. The R180 comes over one. The R90 moves over. Sorry, oh, I'm mistaken. Sorry, these are swapping. I'm doing one of these. And then you've got the R270 and the R90. Perfect, right? That makes sense. And then here we're going to do D, V, D prime, H. Okay, so the D went to the V swapped over to the D prime, H went over here, and the D prime went, and the V went here. Yep. And so then you've got over here R270, R90, R0, and R180. And finally, you've got D prime, H, D, and V, and then R90, R270, R180, and R0. Okay, and so this is the operation table for the dihedral group of order 8. Okay, and so this is something you can use to quickly see what happens when you compose certain elements. And if you have more than 2 elements, you can just reuse the table, right? You can just keep kind of adding to it. Okay, all right, so let's take a look at, there's a couple things in this table, structurally speaking, that are very interesting, right? And before I do that, I want to put some kind of a marker on here. So I'm going to circle this entry right here. Okay, so the circle, just for your reference later so you can remember the order, the circled entry is D equaling H composed of R90. Right, so that tells you that you do R90 first and followed by the H. Okay, so that's just for your benefit. A couple things to notice about this table. And a few things to note about the table. So the first thing is that for any 2 motions done in a sequence, the resulting motion is in the group, isn't it? Right, so if I do any 2 motions, I never get outside the 8 elements that were part of the group, right? We kind of said that at the onset, right? And this table kind of proves it, right? As long as you buy that these are all the motions, but you can confirm that just by checking it if you'd like. So a few things to note: that for any two motions, the resulting motion is in the group. Okay, so the resulting motion is in the group. And what we mean by that is that any 2 motions composed will give you a third motion that is one of the original 8. Right? This is a very important property of groups. This is called closure. Okay, this is called closure, and we'll see that that's part of the definition of a group, is that it must be closed. Okay. Another thing to notice about this is that for any element in the group, any of the 8 elements, composition with the R0 element results in basically a returning of the original element, right? So composing any element with R0 results in a returning of the original element. Or I could say no change. I'll use both terms. So no change is kind of the way it looks in this group anyway, with this physical group. But a better way to think about it is the original element is returned. Right, and what do we mean by that? Well, like this whole top line demonstrates that, right? So an R0 composed of an R90 gives you an R90. V composed of an R0 composed of a V gives you a V, right? So anything composed with R0, you get back the thing you started with. Right. This is another important feature of a group, This is called an identity element. R0 in this context is called the identity element. And so that's another, so you have closure up here, and you've got this idea of an identity element as well. This is another important feature of a group. Okay. The next important thing to note is that for, this may be less obvious, less easy to see. Well, it's actually fairly easy to see. We'll get the table out in a second and look at it. But for each element, there is another element which, when applied, returns the identity element. Okay? So if you look at the table here, every row is going to have the identity element in there. So you've got your R0 here, which an R0 with an R0 gives you an R0. You've got an R0 here, so an R270 and an R90 produce an R0, return the identity. You've got this guy here, R180 and an R180 gives you an R0, and a 270 and a 90 give you a 0. So the rotations are kind of obvious, but then you also have it over here with the flips. So an H and an H gives you an R0, right? So if you flip it, and then you flip it again, you're obviously getting back to where you started. A vertical and a vertical give you an R0. Two diagonals give you an R0, and two off diagonals give you an R0 as well, right? And so every row has the identity element. And so that is an important reality. So for every element, one sec, make sure that's focused. So for every element, there's another element which returns the identity element when applied to it. Right, so we saw R90 equals R0, and we saw D, and D is R0, right? Okay, so for example, okay, these elements are called inverses of one another. They're called inverses of one another. And this is, again, another important property of groups. It'll be part of the definition of a group, is that elements all have inverses. You can think of these elements as undoing each other, kind of like how we use inverse in other contexts. Here it means the same thing, right? They undo each other. Okay? They undo each other. All right. Another thing that you might notice if you start to play with this table a little bit is that some of the elements, for some of the elements, the order does not matter, but for some it does. So for some elements, the order does not matter, but for some it does. Now, sometimes we'll encounter groups where it doesn't matter for any of the elements in the group, and we'll call that kind of group a commutative group, right? And this is not the dihedral group is not a commutative group. But we can see this property in the table for some of the elements. So for example, if I do an R90 composed of R180, sorry, I get an R270. And what you'll find is that it doesn't matter if I do the R180 first or if I do the R90 first. right? So R180 and R90, they commute. We call that commuting. These two elements commute, meaning the order doesn't matter. It's the same usage that we have in other. We've seen the word commute before, commutative property. But sometimes commuting doesn't work. So for example, if you do an H composed of a D, so you do a diagonal flip and then a horizontal flip, you get an R90. You can confirm this by looking at the table. But if you do a horizontal flip first, followed by a diagonal, right? So you do the horizontal and then the diagonal, you actually end up with an R270. And these are obviously not equal, right? So these two elements, H and D, do not commute. Okay. And so D4, because it has elements that do not commute, it's not a commutative group. But we'll see many examples of groups that do commute. Every element commutes, and then we say it's a commutative group. Okay, very cool, very cool. Right, and so the definition of a group, the group being a group, it is not necessary that every element commute, obviously, because this is a group where not every element commutes. Okay. And the other interesting thing about one additional thing that's interesting about this group is that the element compositions are actually associative. Okay, so the compositions for this group are associative, right? So when I say associative, I mean A, B, C equals A, B, C. Right, and so this is actually true for all A, B, C in the dihedral group in D4. All right, let's see an example or two of this. We won't be able to check everything, obviously, but I can point to some examples. Okay, so let's say we have H and then R90 and D. So if you look at the table and you see R90 composed of a D, you'll see that that's H, right? So the R90D is an H. And then an H and an H gets you an R0. Okay, so you could go check the table and confirm that that's true. So what happens if I do the H and the R90 first? Well, the H and the R90 gives you a D. And a D and a D, we know, gives you an R0. So these are equal. Right, so while the order matters, the order in which you do the composition doesn't appear to matter. Well, at least I'm saying it doesn't, and in this example you can see clearly that it doesn't. Right, so if I do these two first and then compose that with a D, I get a D and a D, and I get the same answer. Right, so that's very interesting. Right, so this is associative property. Right, so associativity seems to be something that groups tend to have. And let's see another example. So this would be example 1. What about example 2? Let's say I do a D1, an R90, and an R180. And let's say I do the R90 and the R180 first. Then I get a D, and the R90 and the R180, if you look at the table, that's an R270, isn't it? You could probably not look at the table for that one. But you do have to look for this one. R270 and a D gives you an H. Okay, now what if I do the D and the R90 first instead? D and a diagonal flip followed by, or sorry, a 90-degree rotation followed by a diagonal flip gives you a vertical flip. And a vertical flip composed of an R180 gives you an H. And so again, equal. All right, very good. So this is the associative property. associativity, which we will have heard of. Okay. All right, and so I think that's where we'll leave off with this section. But again, remember, this is just a single example of a group, right, consisting of 8 elements. And the elements of this group are highly tangible, right? You can take any square, just mark the corners of the square, and you can see the structure of this group playing out in just in just the way that the squares move. A square can be flipped and rotated, right? So it's a very physical idea. Okay, and so that's the idea. The key here, the goal was to really kind of help develop some intuition, and we will get into the definition of groups in the coming lectures. But the key things that we wanted to point to here are, is this idea of closure, the identity element, that concept, the commutativity, inverses, right? So those 3 in particular, closure, identity, and inverses, are all part of the definition of a group, which we'll see in the next lecture. Okay. We also want to give some indication of these other ideas, specifically commuting elements and associativity of elements in a group. Okay. And all of these things can be seen with this simple example of the dihedral group of order 8, the symmetries of a square. Okay. All right, so we'll leave it there, and when we come back next time, we'll get into the formal definition of a group, and we'll see lots of examples, and we'll talk through some of the elementary properties. We'll kind of get into the meat of group theory. All right, we'll talk to you all later. Take care.